why don't we get started, Tselil, Schramm, with this sequence.
Thank you for the introduction. So yeah, thanks everyone for coming to my talk, and thanks to the organizers for inviting me. Today I'll be talking about max cut with linear programs. Sherali-Adams strikes back, and this is based on joint work with Ryan O'Donnell. And at a high level, the point of view that I'm coming from is optimization. So many times in optimization, we're interested in optimizing over some complicated set. So here, when I say a set is complicated, I mean it can be complicated in several ways. Like maybe it's not convex, or perhaps it's convex but it has a very large description. And one technique that we have is relaxation, so convex relaxation. So this means we take our complicated set and we relax it and possibly lift it into higher dimensions. So we take it and we embed it into some convex set. And now in this convex set we can optimize efficiently. Okay? But because we took this convex relaxation, there's a loss of accuracy. Right? So if this is kind of the direction that we were trying to optimize in, here this is the true optimum point, and you can see in the relaxation that we get a different point with a possibly larger value if it's a maximization problem. And so what we want to do is we want to understand how much the relaxation cost us. So the goal is to quantify the accuracy, and in particular as a function of the relaxation size, so both the dimension that we go to and the complexity of the description of the relaxation. Okay, so some popular and nice sets include linear programming. So here we are maximizing over the positive orthant subject to linear inequality constraints. Another popular type of nice set is semidefinite programming. So here we're optimizing over the PSD cone, again subject to linear constraints. And yet another extension of these is hyperbolic programming in general. But today LPs and SDPs are going to be the stars of our show, in part because these are the most well studied in the context of discrete optimization. And what we want to understand is we want to understand the relative power of LPs and SDPs. So both of these are hyperbolic cones. That's the connection to today's, to this workshop. So the positive orthant is the hyperbolicity cone of the polynomial product Rn xi in the direction the all ones vector. So and then the PSD cone is the hyperbolicity cone of the determinant of x in the direction of the identity, right? And the PSD cone can be used to capture linear programs. And in general, pretty dramatic separations are known in this power of LPs versus SDPs. So our goal is to quantify accuracy as a function of relaxation size, and it's known that if you want to capture semidefinite programs, in general, you need exponential size linear programs, right? So there are SCPs that have size polynomial in n over n by n PSD matrices, so that you need, if you want to get a constant approximation factor to this spectrohedron, you need a linear program of size at least exponential. Okay, or if you're fluent in extended formulations, there are spectrohedra that have extension complexity n+1 over SDPs and extension complexity exponential over LPs. So here we see this dramatic separation, and the question is, how does this separation play out for classical optimization problems? And is there some way to parameterize the kind of semi-definite programs or linear programs in order to understand what this relationship should be? Yeah.
So is this constant? Is this in the sense of containment of the feasible sets or in the objective values?
Containment of the feasible sets. Okay, good. And I guess tomorrow we'll hear from Nick about the question of getting general hyperbolicity cones in terms of semi-definite programs. So this is the prequel, in some sense, to Nick's talk tomorrow. Okay, so the problem that I'm going to want to focus on is maximum cut. So in max cut, I have an input graph, And the objective is to output the maximum fraction of edge cut over any partition. So I'm trying to find the partition that maximizes the number of cut edges. For example, in this graph, I'm trying to, this is one partition. I can think of assigning +1 to one side of the partition and -1 to the other. All right. And I can express this optimization objective in terms of this following integer program. So I'm taking the sum over all edges, the average over all edges of half times 1 minus xi times xj, where x is our sign. So this is going to be 1 if the vertices are on opposite sides of the cut, and 0 if they're on the same side of the cut. Right, so this is just the fraction of edges cut. Generally, computing max cut is NP hard, so I guess no talk about max cut is complete without seeing this fact. But now what I want to understand is I want to understand how well can I approximate the maximum cut objective. Okay, and what I want is I want a relaxation that produces an upper bound on the value of the maximum cut. And how do I measure the quality of this bound? Well, I measure it in terms of the approximation ratio. So I take the true maximum cut value and I divide it by this upper bound. This is going to be some number in the range of half to 1, right? So 1 means I perfectly approximated the value of the maximum cut. And half is the worst possible approximation factor. This is just because in any graph I can cut at least half of the edges. So it never gets worse than half. Okay, so one of the most famous semi-definite programming results is that the following basic semi-definite program approximates max cut well. So if I take the integer program that I had on the previous slide, and instead of requiring that my variables be on the hypercube, I replace every variable with a unit vector, and I optimize over gram matrices of these vectors with norm 1. Then I get a semi-definite programming relaxation of the following form, and the following dual formulation. Okay, and the upper bound that I would output is just I would output the value of this optimization problem over the gram matrices. So theorem due to Gomez and Williamson is that this approximation ratio is at least 0.878. Okay, so significantly better than the worst that you can do at a half. It turns out that assuming the unique games conjecture, so a complexity theoretic assumption, this is the best approximation factor you can get in polynomial time. Okay, so semi-definite programs are optimal assuming the unique games conjecture. Actually, if you're in the case when the maximum cut has value close to half, then you can do even better with a semi-definite programming relaxation. So you can actually certify close to half. So for graphs with small maximum cuts, you can get approximation factor that's close to 1. All right, so that's it for SDPs. But if we look at the basic semi-definite program, what's it doing? It's using spectral properties of the adjacency matrix. So if D is the diagonal matrix with the degrees on the diagonal, and A is the adjacency matrix, then if you look at the dual formulation of the SDP, the value that it will output is it will output the minimum over diagonal matrices of trace 0 of some scaling factor times the maximum eigenvalue of the degree matrix minus the adjacency matrix plus U. So it optimizes over such U. So it's a very spectral relaxation. Okay? And the question is spectral information necessary? Right? So generally speaking, in order for LPs to capture spectral information accurately, we need exponential size LPs. And the question is, do we really need to have exponential size linear programs in order to get a good approximation ratio? Okay, so linear programming relaxation. So the conventional wisdom is essentially that LPs are not very good at max cut, right? So when you teach undergrads or beginning grad students about linear programming, you show them some nice examples where linear programming works really well, and then what you do is you say, okay, now try to write down a relaxation for max cut. Haha, like you can't do it, you know, they all have factors of 2. Okay, this is definitely how I was taught about linear programming anyway. But actually, I mean, beyond just this exercise that you give to undergrads, there's a good reason for this. So I'm going to kind of explain in sort of a backwards chronological order why, but it makes a little bit more sense. So there's a theorem, a combination of basically 2 theorems due to Chan, Lee, Raghavendra, and Stoyer, and then later Kothari, Mecca, and Raghavendra. that Sherali-Adams is the best possible LP for max cut. Now, okay, what's Sherali-Adams? I'll say more later. But essentially, Sherali-Adams is a family of linear programming relaxations that allow you to start with some basic linear programming relaxation and then systematically strengthen it by adding variables and constraints. So going to higher and higher dimensional constraints to get tighter and tighter relaxations. Okay, so at every level of the Sherali-Adams hierarchy, you get a LP of different size. Okay, and at level D, you have a relaxation of size n to the d. Great. So basically, what was proven, this is the statement of Chan, Lee, Rugavendra, and Sawyer, and Kothari, Mekar, Rugavendra. The statement is a little bit more complicated. But basically, what was shown is that if there's any linear program of size at most n to the d, with approximation ratio at least rho, then if you take level 2D Sherali-Adams, which has size n to the 2d, you get at least as good an approximation factor. So if you don't care about things like quadratic factors in the size of the LP, then Sherali-Adams is basically the best LP that you can have. Okay, and then coupled with this, there are strong lower bounds for Sherali-Adams. So in 2007, De La Vega and Mathieu proved that for any constant number of rounds of Sherali-Adams, there's a sequence of graphs that where the Sherali-Adams gets approximation ratio at most half. Okay, half plus epsilon for constant epsilon. So constant size Sherali-Adams, or constant round Sherali-Adams, polynomial size Sherali-Adams can't do better than half. And then significant strengthening of this theorem came a couple years later due to Charikar, Makarchev, and Makarchev. So essentially what they showed is that even if you take Sherali-Adams at degree n to the delta for delta fixed constant, you can't get approximation ratio better than half, right? So even sub-exponential size LPs can't certify better than half in general. Okay, so already we have a sub-exponential separation between the performance of the SDP of polynomial size and LPs. Okay, and one thing about this proof is that if you look at it, it doesn't clearly hit a natural barrier. Like it's not clear why sub-exponential size should be the correct answer. Okay, and you think, well, we know of cases where there's a truly exponential separation between LPs and SDPs, right? So the question is there a truly exponential separation between LPs and SDPs for max cut? That is, can we prove a linear round or linear degree Sherali-Adams lower bound for max cut? Even for this sequence of graphs, maybe. Okay, so that's one question, motivated question. Here's another motivating question. My secret motivation is trying to understand current technology. So in 2016, Barak et al., including Sam here, showed a new technique for, they introduced a new technique for proving semidefinite programming lower bounds. So this technique is called pseudo-calibration, and they used it in the context of planted clique. And without getting into too much detail, let me just say that pseudo-calibration at a high level is a technique for proving SDP lower bounds using statistical similarity of two distributions with different optimization values. So for example, if you look at the maximum clique problem over two graphs, the set of just uniformly random graphs versus uniformly random graphs where I've planted a k-clique, for some statistics, these are statistically similar, okay? And because of the statistical similarity, you are able to prove SDP lower bounds just basically by showing a feasible SDP solution for a specific relaxation that has too large of an optimization value. So you show an integrality gap. This is a great technique. One of the nice things about it is that it's very general. So we know also that it works for constraint satisfaction problems such as KSAT. Actually, this is in hindsight. If you look at the constraint satisfaction problem lower bounds from the past, it turns out that they too execute this formula without having known about it. So that's really cool. And then for a couple of other problems, we can also show lower bounds using this technique. And probably for many optimization problems, an average case and statistical optimization problems, you could apply the same technique. The problem is, it's very difficult to show that the SDP solution that this pseudo-calibration technique proposes is positive semi-definite, right? So so all of the linear constraints are pretty easy to enforce, but then the positive semi-definiteness step is quite difficult. And what better way to ignore the positive semi-definiteness constraint than to consider LPs instead, right? So that was the secret motivation for thinking about this question. For example, you could ask, can you prove that if you take Gn 1 over n to the 0.99, so Erdős-Rényi random graph with average degree n to the 0.01, that a degree n to the 0.1 Sherali-Adams relaxation won't be able to get an approximation ratio better than half, right? This is because in some sense, if you look at n to the 0.01 random vertices in the graph, they will look like completely unrelated to each other. It'll be a tree or it'll be just a completely random set. And so this is some kind of statistical similarity between graphs with large max cut values and subsets of these graphs, right? So this was kind of the hope at the outset of this project.
How would this question compare with what CMM proved?
So CMM are essentially considering random graphs with constant average degree. And this is slightly denser graphs, like small polynomial average degree. Yeah. Great question. Okay, so this was the kind of motivating thrust for this project. But it turns out that instead of proving lower bounds, what we prove is an upper bound. Okay, so surprise. So suppose that I have a graph where the random walk transition matrix has eigenvalues that are bounded by some parameter 1 over square root delta. Okay, there's going to be a reason why I said it this way that will become apparent in a second. So what we then show is that if you take exponential in log n over log delta round of Sherali-Adams, then you can get an approximation ratio that's like 1 minus 2 to the k. So a good approximation ratio in this many rounds. So let me instantiate this with a specific example. So say that I have a random graph with degree order delta or average degree order delta. Okay, then this condition will hold with high probability. And then if, for example, delta is like n to the 0.01, as would be in this case, then constant level Sherali-Adams will achieve approximation ratio at least 0.99, right? So this means polynomial sized LPs get approximation ratio close to 1 for random graphs with polynomial average degrees. Okay, so this is surprising. I mean, already goal number 2 is wrong, right? So LPs do pretty well for random graphs of polynomial average degree. To me, this came as a big surprise. So even bigger surprise is that the previous lower bounds are in some sense tight. So if you look at the graphs that the Charkar, Makarichev lower bounds were using, basically they were using random delta regular graphs where delta is a constant, okay? And the number of rounds that they prove a lower bound for is something like exponential in log n over log delta where there's a constant out front here, right? So if you take log n over log delta, or exponential in log n over log delta times some constant rounds, the approximation ratio is at most a half. But then we show that if you take a larger constant here, then you can get approximation ratio close to 1, right? So the previous lower bounds are tight as a function of the degree. Yeah?
What's the value of the max cut in these graphs?
So in these graphs, the value of the max cut is going to be something like half plus 1 over square root delta. I mean, I guess order 1 over square root delta.
Okay, so the point is that that number is small enough so it's not trivial.
Yeah. This number.
Yeah.
We can never take this number to be so small that, or so large that the answer will be wrong. But yeah, it's small enough that it's not true. And we can approach the truth like by taking more rounds. Yeah. Okay. Great. So I think that's a big surprise. And now what you can say is, okay, still I want to know if there are graphs where linear many rounds of Sherali-Adams won't certify good bounds, where the approximation ratio will be close to half. And the answer is that maybe such graphs exist, but it doesn't seem like it's these graphs, right? Because I mean, there's some question about if there's a specific delta, like such that I mean, there's some issue of the constant out front here, right? That one needs to be careful with. But it seems like these random regular graphs are not good candidates for showing exponential round lower bounds. for Sherali-Adams. Okay.
So,
Yeah.
so basically that would imply you can get a p-task, yeah? Go back to like
Why?
maybe the previous one? No, sorry, like maybe I missed it. If k,
Only
So-
under the
You
eigenvalue
need,
condition.
yeah, you need this
course.
pseudo-randomness condition in
Or
order to get
dense
such
graph,
a
or-
p-task, yeah. So the requirement is that the eigenvalues of the graph are
Yeah.
bounded.
like, or dense random graphs.
They don't have to be dense. I mean, so notice that even if the graph is sparse, then this is giving a sub-exponential size LP upper bound, right? So the result applies regardless of the graph being dense or not. I mean, this is just the round. But in order to get a polynomial sized LP, then the graph has to be a little bit dense. But it doesn't have to be super dense. I mean, just polynomial degree.
No, I'm just trying to
Yeah.
understand from an algorithmic result, is this, the algorithmic result this is
Oh.
implying, is that already known or is that,
The algorithmic result that this is implying is always weaker than the semi-definite program of size 2, or of size polynomial n at degree 2, right? So the LP is never going to be better than the SDP. This will not get you better than the eigenvalue bound that you would just get with the trivial spectral relaxation. So algorithmically, this isn't giving new faster algorithms for maxcat. This is just, I mean, the thing about this result is it's really a comparison between LPs and SDPs, and it's showing that that the separation that we previously thought was very dramatic, like exponential, is not so dramatic, at least under this pseudo-randomness condition on the graph. So you think there should be an exponential separation between LPs and SDPs. In some cases there is, but this is not one of those cases. Maxcut in graphs with bounded eigenvalues, you have a sub-exponential, most a sub-exponential separation between LPs and SDPs. Yeah. Okay, good. Yeah, great question. Okay, great. So in fact, yeah, these previous lower bounds are tight, and it's possible that sub-exponential LPs can certify non-trivial upper bounds on maxcut in any graph, right? So if you want an exponential lower bound for maxcut, it should come from a different family of graphs. Yeah, another thing that's just surprising, I mean, I guess I have said this a couple of times, but let me just say it again. So here I have some spectral condition on the adjacency matrix of my graph, and from this, I get that the LP has non-trivial performance. And it's pretty surprising that the LP is managing to capture some spectral property of the graph. I mean, to use that in order to certify upper bounds, right? So I think already this is pretty strange. And I guess understanding this better would be nice. Yeah.
So is this 1 over root delta, if you weaken this, can you get some, does it degrade nicely, or you really need the 1 over root delta?
I mean, I just chose that, I mean, here there's a log delta, so...
Okay, so really any bound on that, it'll give you something there.
Yeah. I mean, whether I
Oh,
use
see,
the delta is just some parameter, but I just chose it because
Doesn't have to be the degree, okay.
because of the degree, yeah.
Okay.
Okay, great. And let me also say that this isn't only true for maxcut, so we can get similar results for Boolean constraint satisfaction problems, and also for, I mean, this isn't in the write-up online, but with small modification, you can get similar results for vertex cover and independent set and clique. So it really seems like this is a more general phenomenon for optimization over the hypercube. Yeah.
How about like more spectrally tight problems like sparse cut or something?
Yeah, we don't. I mean, for sparse cut, I'm not sure what the issue is. I mean, there, I would worry about how to tie the global constraint in. But yeah, but we didn't. I mean, we didn't think about sparse cut.
Is there a barrier to doing that, or?
I think that one would just need. I mean, it's clear that you couldn't do just a small modification to what we've already done. Like there would need to be another idea, but I don't know if there's a barrier. I don't know.
You have a different LP, like the flow LP, or
Right. Yeah, I don't know. Yeah, we didn't. I mean, it's not clear to me that there's a barrier or no barrier, but it wouldn't follow easily from what we've already done, I think. Okay, great. So let me just say for random constraint satisfaction problems, what we get. So in random constraint satisfaction problems, say that I have a SAT, for example. usually the model is that I sample a random formula by choosing m random clauses. And so let's say that this is the axis in which I increase m. So what we show is that let's say that k is even. What we show is that if you have at least n to the k over 2 plus epsilon satisfying or constraints that you sample, then an LP can certify LPs, polysize LPs approximate the value well. Okay, and what I want to do is I want to compare this to what semidefinite programs can do, right? So in semidefinite programs, you need n to the k over 2 constraints in order to certify the value well. So this is the regime where SCPs work. Polysize. Okay, and I think this is really interesting because a priori, what I thought would be true is that you'd need something like n to the k constraints for LPs. So this was a hypothesis. I guess this might be kind of small for people to see, but at least maybe the lines are big enough. So the point is that here we see a separation in the kind of the more constraints that you have, the easier it is to certify upper bounds. And there's a surprisingly small difference between what SCPs and LPs can do, right? So in graphs, this would correspond to degree, right? There's like, and if you look at a difference between a constant average degree and a polynomial average degree, it might seem very dramatic. But I think if you think about it in the context of constraint satisfaction problems, it actually seems a little bit less stringent, right? So really the separation between LPs and SCPs is much less than what we would have expected.
So what's equivalent in here of your, before you were getting this from this eigenvalue gap.
Yeah.
That was coming from,
right.
From the degree. So here, what's the equivalent? What's the parameter?
So here the equivalent thing is the eigenvalue gap of the, you can take the kind of constraint tensor, right, and you can flatten it to a matrix. Mm-hmm. And that's where it comes from. It's the eigenvalue of this flattened matrix.
That comes using the k, or you're looking at k sub, or what controls that gap?
The thing that controls that gap is the density of this tensor. Yeah. So if the tensor isn't dense enough, the eigenvalue will be kind of large as when you divide by the number of constraints, and then yeah. Okay, great. So I guess this is just to demonstrate that again, like a surprising anti-separation between LPs and SCPs, at least if you are properly tuning the kind of difficulty parameter of the problem. Okay, so now at this point in the talk, I guess I will tell you the proof, unless there are more questions about the setup. Okay, so let me tell you the proof. So the first thing I need to do in order to tell you the proof is to define Sherali-Adams. Okay, so let me just say what Sherali-Adams is. So in Sherali-Adams, at level D, this is a relaxation for optimization over the hypercube in n dimensions. What I'm going to do is I'm going to have n choose d variables, one for each subset of n variables of size at most d, right? So I'm going to get what I'll call the pseudo expectation of every monomial of size at most d. Okay, and what I'll do is I'll include linear constraints so that every subset of d variables will specify a local distribution over Boolean assignments, right? So if I look at the moments for any subset of d variables, these are consistent with some actual distribution over Boolean variables. So and my claim is that I can achieve this with an LP. Why? So if I have a joint distribution over d Boolean variables, then I can uniquely specify d with only 2 to the d numbers, right? So this is just by writing the probability of each outcome. Okay. And I can, if I have 2 to the d numbers, linear constraints can ensure that these are just a distribution, because all I need is that the sum of the probabilities is 1, that the probabilities are non-negative. All right, and then the final ingredient is just to realize that these probabilities can be written in the monomial basis. Okay, so it's enough for me to write down the expectation of any monomial, and from this I can get these probabilities, and so if I constrain the monomials, this will give me a distribution. So my variables are just going to be the kind of pseudo expectations for every subset of d variables, and from these I can ensure that I have a global LP solution such that every subset of d variables corresponds to an actual distribution. So that's degree D Sherali-Adams. D is the number of the size of the subsets of variables that obey the local distribution constraints. Okay, so in the integer program, I wanted a global distribution over cuts over the hypercube that maximizes the expected fraction of cut edges. Okay, so it's like here I would be optimizing for a expectation operator that specifies the moments of this distribution. And in my relaxation, I'm just going to require that the distribution be d-local. Right, so I solve for these pseudo expectation values for the d-local. Okay, good. So yeah, and then rephrasing our theorem, as long as I have my eigenvalues bounded by 1 over square root delta, then exponential in log 1 over epsilon log n over log delta rounds of Sherali-Adams will give will certify that the eigenvalue is at most half plus epsilon. So for such graphs, sorry, not the eigenvalue. For such graphs, the max cut value is at most half plus 1 over square root delta. Okay, and what we'll certify is half plus epsilon for any epsilon larger than 1 over square root delta. So this is going to be our goal. And basically what our goal is going to be to lower bound the expectation over an edge in the graph of the pseudo correlation of two variables, right? So this is like the objective value of the LP. So if, yeah.
The epsilon can never be less than 1 over square delta?
It can never be less than 1 over square root delta because this would be less than the true max cut value.
Okay, because for random graphs, the eigenvalue bound is tight.
For a graph that has eigenvalues that are 1 over square root delta,
Yeah.
that's tight, just because of the spectral relaxation.
But there are graphs for which the spectral bound is not tight, right?
Yes. Yeah.
Okay.
But we can never get better than the spectral bound. Yeah. Yeah. I mean, I guess in exponentially many rounds we will, but yeah. Great. So the Sherali-Adams at degree D value for the graph is just the expectation over edges in the graph of half times 1 minus this pseudo correlation, and we want to prove that this is at most half times 1 plus epsilon. So our goal is really just going to be to lower bound the average pseudo correlation across an edge. Okay. And how are we going to do this? We're going to use make use of the following fact. So let's say that I have any d variables in the degree D Sherali-Adams relaxation, and let's say that I have a positive semidefinite matrix M, a d by d positive semidefinite matrix M. So here, because I have at most d variables, I know that the pseudo expectation of this quadratic form with M is going to be non-negative. Okay, and the reason is that in an actual distribution, ZZ for an actual distribution ZZ transpose, the expectation of ZZ transpose is going to be positive semi-definite, right? So this is just going to be a quadratic form in expectation. So we lower bound it by 0. I can also write this as a linear form in the pseudo expectations of the pairs, right? The pseudo correlations. And now, even if I take a expectation over subsets of d variables at a time, this will still be true, right? Because I'm just by I'm summing positive numbers, so I'll get something negative. So what our plan is going to be is it's going to be to choose a distribution over subsets of at most d variables in the graph, and a specific positive semi-definite matrix M, so that from d locality we'll get this expected quadratic form is non-zero. Okay, but by our choice of this distribution and the choice of this matrix, we're going to get that this is equal to the expectation across an edge in the graph of the pseudo correlation across the edge plus some small constant epsilon, right? So this will give us our goal.
So you,
Yeah.
if you had wanted, you could have chosen M to depend on the subset H, is that right?
If we had wanted, we could have
But
done
you
it.
didn't have to do
But we
it.
didn't do it.
Okay.
Yeah. Yeah, it's going to be a fixed matrix. Okay, so this is, I mean, this is just our syntactic goal. Find a PSD matrix M and a distribution over subsets of variables so that we get this, so that, you know, this quadratic form gives us this value. Okay, and then by d locality we'll have that it's at most 0, and that will give us our lower bound. Great, so now let me tell you how we're going to choose this subset or this distribution over subsets. What we're going to do is we're going to use random walks. Okay, so in a random walk in a graph, what I do is I pick a vertex, and then at every step I pick one of its neighbors and I jump to it uniformly random. This walk has a stationary distribution, and you know, it's given by this, and the proof of this is simple, but I'm not going to do it. What we're going to do is we're going to define the following distribution over pairs of vertices in the graph. Okay, so define dt to be the distribution over pairs in the graph, sampled as follows. First, I sample a vertex according to the uniform measure, the stationary measure. And then what I'm going to do is I'm going to take a t-step random walk, and I take the final vertex that I land at to be ut. Okay, so a fact is that if I take d1 and I take a pair of vertices sampled according to d1, this is like a uniformly random edge in the graph because I'm picking a vertex according to the stationary measure, and then I'm jumping to one of its neighbors. This is a uniform edge in the graph. So this is just basically a calculation. Okay, another fact, which is a little bit less trivial but also not very difficult, is that if I take t to be something like log n over log delta, then u0 and u1 are going to be close to a uniformly random pair of vertices in the graph. So basically, if I take log n over log delta steps of a random walk, I'm going to mix to the stationary measure up to total variation distance little of 1. This is equivalent to saying that for any vertex in the graph A, if I take the indicator for A and I apply the random walk operator to the power t, I get close to pi in infinity norm or whatever you'd like. And the proof here is simple as well. So basically what I do is I take this indicator for the vertex A and I decompose it spectrally according to the eigenvectors of my random walk matrix. And if I take the tth power, I'll get to the tth power of the eigenvalue. What I can do is I can write this as some factor times the stationary measure, right? Stationary measure has eigenvalue 1. And let's say that all of the other eigenvalues are at most 1 over delta, so I'll get something like this, right? And here, the rest, I mean, these are vectors of the most unit norm, so if I take t to be at least log n over log delta, this will be little of 1, and I'm getting really close to the stationary measure. Okay, so from this we get the following fact. If I take t to be at least log n over log delta, then u0 and ut are distributed essentially like independent samples from the stationary measure on the graph. Okay, these two facts are basically going to be the facts that we'll use about such embeddings. So great. So now what we're doing is we're going to choose our distribution h according to what I'll call random walk embeddings. So we're going to define h to be a distribution over subgraphs of this graph, sampled as follows. We'll sample a kind of root vertex, u0 according to the stationary measure. Okay, and then we're going to take k independent t steps random walk from u, right? So and the set of vertices that we see is going to be the subset of d variables that we're looking at. So we're basically embedding this spider, right? It's like the body of the spider and then k legs of length t into the input graph. Okay, it's random embedding. Great. And my claim is that if I take any two neighbors in this embedding, they're distributed like a uniformly random edge in the graph. Just because they're distributed according to d1, right? It's because like I pick a vertex according to the stationary measure, and then I take one random walk step from it.
So the graph includes u0, or you forget about u0 and you look at all?
The graph will include every vertex that I see in the...
Including u0?
Including u0, yeah.
And the ones along the path.
And the ones along the path,
Oh,
yeah.
okay.
Yeah. So the neighbors are going to be distributed like IID edges in the graph, and the endpoints, the embeddings of the endpoints, like UT1 versus UT2, these are going to be like uniformly random pairs because I pick T to be large enough so that it's like the mixing time for the random walk. Okay. So there'll be like IID samples from the stationary measure. Okay, these are basically the only facts that I'll need. So for the case of demonstration, let's fix T to be 1, right? So let's say that we're in a case where walks of length 2 mix. So the endpoints of the star will be like uniform samples from the stationary measure. So what I'm doing is I'm embedding a K star into the graph. So now let's look at the distribution that I get from, or the expectation of the vector ZZ transpose, where I pick my variables according to this embedding. Right. So if I look at this, I'm going to get a block matrix of the following form. In these entries, these correspond to the correlation, the pseudo-correlation between the kind of root and a child. This will be like the pseudo-correlation of a uniformly random edge in the graph. Right? This is because walks of length 1 are like uniformly random edges in the graph. Okay. So that's good because I want to have my quadratic form include the pseudo-correlation of a uniformly random edge in the graph. The diagonals are going to be 1 just because it's a Boolean distribution. It's a relaxation for a Boolean distribution. Okay, and then here for the off diagonals, which correspond to pairs of the kind of spokes of the star, these are like uniform pairs. This is the pseudo-correlation of a uniform pair in the graph, approximately, up to small total variation distance. And humor me for a second and assume that this quantity is 0. Okay, so it kind of doesn't make sense that you would have that if you pick a uniform pair of vertices in the graph that they have large pseudo-correlation in magnitude one way or the other, but this won't be important, but just for now assume that it's 0. So now what we can do is we can choose a matrix M so that we can get such an inequality. And our matrix M is going to be the following positive semidefinite matrix. I'm going to take VV transpose where V is a vector, where V0 is 1, so V0 kind of corresponds to the entry of the root, and all the other entries are 1 over square root k. And now I will have, from the fact that I have d-local distributions, that the expectation over such graphs times this matrix is non-negative. Okay, and if I write this out, I'll get a bunch of terms. So I have, maybe I'll skip this. I'll go kind of quickly over this part. But essentially, I just take the inner product between these two matrices, and I get an expression that looks like this. So I'll have, Sam, are you okay?
So in some sense, like there was something here about M that depended on how the random embedding looked, right? Because there's this special row and column, and I had to make sure that M lined up, the M special row and column lines up with this guy. So I had to look at like it's not just quite a subset H. It's like the subset specifies who's in the middle.
Yeah, the order matters. Yeah.
Okay.
But it's not the case that I need a different M for every H. That's how I interpreted your previous question, right? So
Yeah. No, my previous question was not this refined,
okay.
But now I'm understanding that you need to like reorder. Like I could think of it as either picking H with an order or reordering the columns and rows of M appropriately to match who landed in the middle of the star.
Yeah.
Okay.
So the form of M will depend on the way that this star looks.
Thanks.
Right, and then just if I take the quadratic form of these matrices, it's not difficult, but it's also not an interesting calculation to show that you'll get some numbers, and you'll have a term here that depends on the average pseudo-correlation across an edge in the graph, right? Because that comes from these from the first row and the first column. Okay, and then great. So now if you simplify this expression, you'll get a lower bound on the average pseudo-correlation across an edge of -1 over square root k. And as you take k larger and larger, this is a better and better, smaller and smaller value of epsilon here. Okay, so this is how we do it. If you don't want to have the value here be 0, what you do is you take a slightly, in order to not assume this, we take a slightly more complicated embedding. So instead of looking at one star, we look at pairs of stars independently being embedded at the same time. Similar things will happen if you look at the expectation over the subset now corresponding to 2 stars. You'll get such a matrix, where you still have entries that correspond to the average pseudo-correlation across an edge. You have entries that are 1, and then you have entries that are like uniformly random pairs in the graph. Okay, and now you just choose a slightly more complicated matrix M so that these entries will cancel with these entries, right? So this is where the uniformity assumption matters, or not the uniformity assumption, but the fact that we chose T to be large enough to get uniformly random pairs matters. Okay, and we follow the same plan, and we get this lower bound. And if you want to make T larger than 1, what you do is you just take, instead of taking stars, you take longer arms, right? So that you get uniform random, and then same thing will happen. You'll have a matrix, uniformly random edge in the graph, uniformly random pairs. You just choose a more complicated PSD certificate, but you follow basically the same plan, and you get this dependence, right? So here now the exponent of k depends on t. And basically what you do is you choose k, the number of arms, to be 1 over epsilon to the t. Okay, and you choose t to be log n over log delta, and you can certify a lower bound of epsilon. So this is where the parameter depends.
So is the only place using spectral information to reason about the distribution of these spiders?
Yes, the only place where spectral information is being used is to reason about the mixing time of random walks, right? And what you really want is you want to know what radius do you have to go in order to see uniformly random pairs of vertices. Yeah, exactly. Okay, great. So now I'll conclude because Pablo is giving me angry eyes. So yeah, the conclusion is basically TLDR in graphs with small eigenvalues. Small LPs can solve max cuts, smaller LPs than we expected. Okay, and I think this leaves many interesting questions open. So one question is, can we strengthen this result? Right, so for SDPs, we know that if I have a graph in which the max cut has value close to half, you can certify that with an SDP. The question is, can you do this for LPs as well, using some kind of spectral decomposition of the graph? So this would be nice to know. Another question is, what is the linear extension complexity of maximum cut? Are there graphs that certify that you really need LPs of size exponential in order to match the performance of an SDP? And then finally, one question is, how do we compare LPs and SCPs in general for statistical problems? Is there a way to understand pseudo-calibration through the comparison between LPs and SCPs? I'm happy to chat about any of these offline, and thanks for your attention.
Questions or comments on Tselil? Yep.
So if I were to sample these spiders by taking a not backtracking random walk instead of a regular random walk, is there some improvement that I get given that these make faster? Or I use spectral information to different operating?
So I don't know. I mean, it depends. I'm not sure if there's some improvement, but I guess that because the lower bounds of CMM match ours up to constant factor, it might only be. I mean, it's possible you could get some kind of constant factor improvement, but not really. But yeah, we didn't think about it at all. So.
I mean, I was just so the key idea is that because the walk mixes fast, the pair correlation is also a local quantity.
Yes. Yes.
Because the edge correlation is always a local quantity.
Yes, edge correlation is always a local quantity.
So can one interpret this? I mean, I'm not sure if this is correct, but like when you have this spectral gap, that you can certify somehow a spectral bound using some kind of sparse eigenvector?
Why sparse?
Because somehow isn't like your subset?
Oh, because it's submatrices?
Yeah.
So one thing that I'll say is that it does seem important that you have if you wanted to certify it for a vector of norm square root n over the unit sphere rather than a balanced vector of norm square root n, then it would be a little bit, I think there would be some issue with scaling factors, right? Because, I mean, this works for Boolean vectors, and the Booleanity assumption is a little bit important Right, you need that you can't
Yes,
get too much
yes,
value
yes.
for submatrices.
Right, yeah,
Yeah.
yeah, I cannot just use.
Right, but if you, I mean, if you do assume that you have balanced vectors and you're looking at sparse subvectors to certify, then it does work. Like instead of enforcing the Sherali-Adams constraints, what you could do is you could enforce local PSD-ness constraints on matrices of size d by d, and also the diagonal being 1, and that would be enough. Yeah.
And maybe it's not that it's a sparse eigenvector, but I think you're showing that some PSD matrix has a local decomposition,
Yeah.
like a local Cholesky factorization.
Yeah.
It factors as a bunch of sparse matrices.
I think that's true.
Somewhere inside it seems like, I mean, maybe we can talk about this. but-
Yeah.
Yeah, you're right, it's more a sum.
Yeah.
Yeah, you might have a dense matrix, but it's
Right. Yeah,
factors
yeah.
as a some
Mhm.
unanticipated.
Other questions or comments?
Seems conceivable this might work if you have only a few small eigenvalues. Like if you have one bad cut,
Yeah, right. So
there
it's,
might still be some way to.
I guess that, are you just saying that there could be some kind of spectral decomposition,
Yeah.
and then yeah, I think that's true, right?
I mean,
Yeah.
it wouldn't just be the mixing time analysis, but
Right.
you could figure out the pair correlation maybe by choosing a few different spiders.
Yeah, I think if there's a simple, I think if there's a simple way to decompose the graph and to then choose spiders within those
Yeah,
parts, then it
yeah.
would be fine. Yeah. But the question is how simple is this decomposition going to be in terms of the spectrum? Yeah.
Last questions? Good, so let's thank Tselil again. We have a 20-minute break, we'll resume 11:45.